students. In the previous video, we learned about the expression for electric field intensity of a charge, okay, of a point charge. Okay, we also got the expression for electric field intensity due to a point charge that comes out to be vector E is equal to 1 by 4 pi epsilon Q by R square into R cap. Unlike the Coulomb's force, okay, it is 1 by 4 pi epsilon naught Q1 Q2 divided by R square, whereas here it is just the charge, source charge Q, okay, the test charge Q0 gets cancelled, so it will be 1 by 4 pi epsilon Q divided by R square into R cap, okay. Now, we shall continue with the next topic. What happens to the expression for intensity of an electric field when the distribution of charge is not a point charge? Okay, if it is not a point charge and it is continuously distributed over a surface area, over some volume of any conductor, anything. Okay, what is that expression? So, based on this, so here we are going to study about the continuous distribution of the charges over a surface, over a line or a volume. Okay. So now to get an expression, the charge distribution, continuous charge distribution may be of three types. One is the first one is one dimensional, two dimensional and the three dimensional. Okay. Based on that we have linear charge density or linear charge distribution, surface charge distribution and volume charge distribution. Okay, based on the one dimensional, two dimensional, three dimensional, we have linear charge distribution, surface charge distribution and volume charge distribution. So first we shall concentrate on the linear charge distribution or a linear charge density. Let us now write it as linear charge distribution. Okay. So, let us consider a conductor or a line charge or a straight charge density lambda. Let us consider a line charge or of a charge density, okay, lambda. Yes guys. Let us consider, in order to get an expression for intensity of an electric field in a linear charge distribution, let us consider a line charge, okay, a line where the charges will be distributed continuously. Here I have considered a positive charge. It has been distributed continuously, okay, of having a length L, in order to calculate the charge distribution over entire length. So first initially we shall consider a small area, a small length dl, then we shall apply it by integrating to the entire length into the entire line charge. Okay, so first what we shall do means, let there be a line charge of linear charge density lambda. Linear charge density lambda. Linear charge density means it's nothing but charge per unit length. Charge per length. Charge per length. This is the linear charge density. Okay. Or else I can also write this to be lambda is equal to charge per length. See, I said you right. Instead of considering the entire length of charge of entire length, first we should consider small length so that it will be easy for me to calculate for the bigger one. Okay, by integrating. Integration means adding, right? So by easily integrating to the entire length, we can calculate it. So let dl be the small length across a length of a linear charge. Okay, let dl be the small length and the charge distribution over this length, this infinitesimally small length, then the charge distribution over the infinitesimally small length be dq. Then the linear charge density can be written as, lambda is equal to dq by dl. Lambda is equal to what? Dq by dl. Okay, next let r1 be the position vector from the origin to the point dl, infinitesimally small element dl, and r2 be the position vector to the point p, from origin to the point B. Let it be the position vector be taken as r2, vector r2, where the point P is the that is the point where we have to calculate the electric field intensity due to this charge distribution, okay. So that test charge be taken as Q naught, So based on this knowledge, so how can we write the expression for Coulomb's force? We know that the Coulomb's force expression is F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square, okay, where Q1 and Q2 are the two point charges, whereas here I said we are not considering only one point charge. Instead is a continuous distribution of the charges, right? So in order to make it easier, we have considered small infinitesimal small element dl having the charge dq. So the two charges become here are dq and q naught, okay. So the expression becomes F is equal to, okay, that is also small force, right? So it will be vector dF is equal to 1 by 4 pi epsilon naught. What are the two charges, guys? Here the two charges are, one is dq along a small infinitesimal small length dl, and one more is q naught divided by, okay, the distance between them, that is r21. See, this is r1 and this is r2, and if I want this perpendicular distance means r21, isn't it? R21, okay. Charge on the force on charge q naught due to dq, okay. So it will be, we can write the expression to be r21 if it is r21 cap r21 square, correct? Correct, students. If it was a vector r21, then it would have become r21 cube, okay, but here I have considered a unit vector, so it will be vector df is equal to 1 by 4 pi epsilon naught dq dq naught divided by r21 square into r21 cap, okay. Clear, guys? Now how to apply this to the linear charge density expression? We know that the linear charge density lambda is equal to, we have obtained, right, lambda is equal to what? It is a charge per unit length, or else I can write this dq by dl, correct? dq by dl, or else I can write dq is equal to lambda into dl. Now can I consider this in equation star? Can I write, because I want an expression for Coulomb force with respect to the linear charge density. I said you right, instead of calculating to the entire small element of over the entire length of a conductor, instead we'll take a small length and then we should calculate it. So substitute that, what we are going to get? We are going to get that to be as vector F is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. In the place of dq I am gonna write L lambda dl divided by r21 square into r21 cap, okay. This is for the small length dl, okay. If I want to calculate for the entire length, can I write it as integral of for the entire length? Can we write like that? Yes, definitely we can write. So this was an expression for Coulomb force, but our intention is to get an expression for electric field intensity, okay, electric field intensity. So please make a note of it. Since I don't have space, I'll write it, okay, I'll try to write it here. See, we have an expression for electric field intensity is nothing but force per Coulomb force per test charge q naught, Coulomb force per test charge q naught. So we can write that to be as 1 by 4 pi epsilon naught integral of, here we have q naught also, right? Yeah, so it will be what? Q naught by 4 pi epsilon naught integral of over the length L lambda dl by r21 square into r21 cap whole divided by q naught, or else can I write it as into 1 by q naught. It's nothing but the same, right? So q naught gets cancelled. So let me repeat, if you have made a note of it, I'll write it. Can I clean it? Yes. So the electric field density E will be equal to 1 by 4 pi epsilon naught integral over a length L lambda dl, where lambda is the linear charge density, r21 is a position vector, and r21 cap. So the expression for the electric field intensity of a linear charge distribution comes out to be vector E is equal to 1 by 4 pi epsilon naught integral of line integral. It is actually, it's a line integral of lambda dl divided by r21 square into r21 cap. For 2 marks it might be asked. Please be aware of it. If you are clear with that, I'll move to the next one. Shall I, students? Yes, students. Now the next part is, as I said you, the charge distribution might be of 1-dimensional, 2-dimensional, 3 dimensions. Okay. In the same manner, now I am going to study about the charge distribution over a 2-dimensional motion. Okay. So for that, let me consider a surface area of yes, a surface of area yes. Okay, as I said, the charges have been continuously distributed over a entire surface of this conductor. Okay, so over the entire surface of this thing, it has been distributed continuously. But my intention is to calculate the electric field intensity, expression for electric intensity due to this surface area on a test charge Q naught at a point P. Okay, on a test charge Q naught at a point P. So what are all the things that we have to consider is, in order to consider that, let us consider surface area yes. In order to calculate to the entire surface area, first let me consider small surface area ds. Okay, small surface area ds. Okay, and let r1 be the position vector from the origin to the small surface area, infinitesimally small surface area ds, and r2 vector, r2 be the position vector from origin to the point P where the electric field intensity has to be calculated, and r21 vector, r21 be the position vector between the surface area ds and the charge Q naught. Okay, so in order to calculate that, first whereas in the linear charges distribution we studied about the linear charge density, whereas here we are going to study about the surface charge density. Okay, linear charge density was denoted by letter lambda, whereas the surface charge density is denoted by letter sigma. Okay, as the linear charge density stated, it is also sigma is equal to charge by area, where the linear charge is charged by length, whereas here it is charged by surface area. So we can write that as the charge is equal to sigma into ds. I have considered an infinitesimally small surface area, so it will be small charge dq is equal to sigma into ds. Okay, but that is not my concern of study right now. My concern of study is to get an expression for electric field intensity E. We know that the electric field intensity is F by Q naught. Okay, vector F by Q naught. So if I want to get the expression for E, means I should know the Coulomb's force F. Okay, so what is the full Coulomb